Okay, so today we're going to go over vector addition, or at least we're going to start it. Okay, we're not going to get into like the really complex, hairy stuff until Monday. Okay, but we'll get into kind of the basics, the principles of vector addition, which is going to be an important kind of overarching concept. Okay, in Unit 1 and in Unit 2. Right? We've talked about scalar and vector quantities before. Okay, scalar quantities don't have direction. Okay, they just have a magnitude, but vector quantities have magnitude and direction, which means when I'm adding them, I need to take that into account. Thus far, the only vector quantities we've added are the type that are referred to as collinear. Okay, collinear means they share a line, or they're on the line, or on the same line, or they're one-dimensional, like north and south, okay, or right and left. They're on the same line. There's a positive and a negative value. Okay? It becomes a bit more complex when we start taking right and left turns, or angled turns. Okay, not 90 degrees, but some other angle other than 90 degrees. Okay, then things become a bit more complex. So what we're going to go over today are the basic principles of how to do vector addition using simple vectors, collinear and perpendicular. Okay, and then we'll start applying that to angled vectors of all kinds starting next week. Okay, so that's when trig will start coming into play a little bit today, but it'll be huge starting next week. All right. So first off, what are collinear vectors? They're vectors that are along the same line. So this person went east, and then they went east, and then they went west. Those are collinear vectors. Okay. All types of vectors are added by placing them tail to head. Okay. What I mean by that is when we draw a vector diagram, draw a picture of what's happening, we place the vectors in order. Okay? This one happened first, then this one happened, then this one happened. All right? So a vector diagram ends up looking something like this. So if I have an object that went east, okay, I would draw it like that, okay, and then I would put the next one on the head of that. Okay, so the tail of the next vector, okay, goes on the head of that one. Okay, I got to line my board. Okay, so it looks like that. Does that make sense to everybody? Probably doesn't because the board's out of alignment. It's all crooked. Okay, let's try that again. So I've got this first vector here. Okay, the person went east, and then they went east again, but not quite as far. So I draw that next vector on the head of that one. Okay, and then if they turn south after that, okay, then I would draw the tail of that next vector onto the head of the last one and do this. Okay, it's basically like I'm drawing a picture or telling the story, okay, with arrows. Okay, as that trick goes on and on. All right. The worst thing you can do is this. All right. If a question says a person goes north and then goes east, I often have people draw that like this. They draw the north part, and then they do this. What is that saying that person did?
Go north, go back, and then go east again?
No, it means they split in half, and half of them went north, and half of them, they were Don Quixote, who got on his horse and rode off in all directions. Okay? You can't do that. Okay? That's what this is saying. It's saying from the starting point, you did this. You're like the scarecrow in The Wizard of Oz. Right? Some people like to go both ways. Okay? Yeah, you can't do that, okay, in physics. You can go one way and then another. Okay? The other problem is, if I draw this way, which is the correct way, right, then I can draw a line from beginning to end that represents my overall displacement. Okay? This would be my final position, and this would be my initial position. Everybody with me there? How do I do that if I draw them tail to tail? I can't, right? Essentially, like if I went east and then south, I would end up going southeast. That makes sense. Okay? If I draw my diagram like this, saying I went north and east, and then I connect the two, which way does it say I went? Southeast. Well, that doesn't make any sense. I went north and east. How could I end up southeast? Okay? So that's why we want to always draw them tail to head, so that we're adding on to the story, okay? And at the end, we get like the actual overall displacement. Okay? This would, if I added red and black and green, that would be my total distance. Okay? But blue would be my displacement. Okay? Straight line, distance, and direction from start to finish. Now for the direction, I would need to calculate this angle in here. Okay? Would I be able to do that if I knew the other sides of the triangle? That's where we're going. Okay? You're going to have to do a little bit of trigonometry in order to get our angles, a little bit of Pythagorean theorem, okay, stuff like that. Okay, so that's what we mean by tail to head, so that's point number 2. Okay, understand that vector quantities obviously have magnitude and direction, and that all vector quantities are added in the same way. All the examples I did here were all of like position and displacement, okay, but velocity is added this way, acceleration is added this way, forces are added this way, any vector quantity. Okay, you draw the picture the same way, you do all the math the same way, and at the end, you put different units on it. Okay, so if this was all displacement stuff, my end units would be meters. If it was all forces, my end units would be newtons, but the math would be identical. Okay, everybody with me there? All right, so a vector quantity deals with both magnitude and direction. Okay, we already know that. Okay, direction is an important characteristic of vectors, so we represent any vector quantity as an arrow. Okay, so anytime we are given like, a displacement or a velocity or an acceleration, we represent that with an arrow. Okay, and the direction of the arrow gives the direction of the vector. The length of the arrow gives its magnitude. Right? So if I had a trip where I went 10 kilometers and then 20 kilometers, okay, my 20 kilometer vector should be twice as long as the first one. Okay? Now, do you need to actually like measure out and do all of this to scale when you're drawing your diagrams?
Yeah.
No, actually you don't. But then everyone, when I ask that question, says yes. Oh, that would be super important. Actually, it's not. Okay? As long as you are at least keeping track of the scale a little bit, okay, and not drawing lines ridiculously out of proportion, your diagrams will be fine. Okay? It takes way too long to actually physically measure everything and draw it that way, so we don't. Okay? But if I'm saying that I have a 2 kilometer vector angled 30 degrees north of east, it should look like that. Okay? And a 4 kilometer vector going due north should be twice as long and go north. Okay? Everybody follow me there? All right, so that's the thing we need to remember about drawing vectors is that, okay, we draw them and their representation is that their direction is where they point, okay, and their length is how big they are. Okay, everybody all right with that idea? Okay, now, referring to directions, okay, we talked about this the other day, but I want to quickly review it. This angle here, because I'm given a compass, is 30 degrees north of east. Okay, it's not 30 degrees northeast, okay, it's 30 degrees north of east. How do I know that?
Because the 30 degrees measured up from where east is.
Right. The degrees are measured from east, okay? The little angle arc that I drew in there is touching east, okay? So it's measured in a northerly direction from east, or north of east, okay? 30 degrees east of north, okay? So this would be due north. 30 degrees east of north would be somewhere along that line. Okay? This angle here would be 30 degrees east of north. Right? So we do have to kind of know our compass directions a little bit. Okay. And then obviously the next part here is it's logical to use the length of the arrow, okay, in the figure to represent the magnitude of the displacement vector. So a 4 kilometer vector would be twice as long. Okay? So the length of the arrow is proportional to the magnitude of the vector. Okay. That's the easy stuff, really easy stuff. Okay, how to draw arrows and make them represent things. Okay, super easy. All right, now when we have to add one vector to another, okay, we do it in order. This one happened, then this one happened. I put the tail of the second on the head of the first. That's drawing them tail to head. Okay? It is absolutely crucial you always draw your vectors that way. It's probably the most common mistake that I see when people draw vector diagrams is to not do it that way. All right? Especially when we get into forces. Okay? People really screw it up for some reason, even though it's no different than what we were doing before. Okay? So we've got, for this example here, okay, the car moves 275 meters due east and then moves 125 meters due east after that. Okay, so our first vector is this blue line here. Okay, this one is the 275 meter one. Okay, and then we've got the 125 meter vector here. Okay, we drew them tail to head. What's our total displacement? 400 meters. Okay, we added them together because they were both in the same direction. Okay, if that second vector had been 125 meters west, then it would have been drawn like this. Okay, how would I figure out my displacement now? Subtraction will make the 125 negative, because you'll notice the title of this is vector addition. Okay, we never say vector subtraction. Okay, we always add everything. We just make one thing negative and the other positive. Right. So in this case, then we would be looking at 150 meters east as our total displacement there. All right, everybody okay with the collinear ones? You've been doing those since Science 10. Okay, I mean, you didn't necessarily know it. Okay, but anytime you've got something going up and down, that's what you were doing. All right. Okay, so this is just saying what we did here. Okay, the tail to head thing. Okay, all vector addition is done tail to head, regardless of whether it's position, velocity, acceleration, okay, or what have you. All right, now let's say we've got this situation. Now the vectors are perpendicular. So I have the initial 275 meter long vector going due east, but then after that, the object turns and goes north. Okay, and it goes north for 125 meters. Okay. Now if I want to calculate the total displacement, it's still a line that connects the initial position to the final position. Okay, that doesn't change. That's still what displacement is. It's the definition of displacement. But now, I can't just add these two numbers together to get it anymore, can I? What am I going to have to do instead? Right, I have to use the Greek e. Okay? Pythagoras spent his whole life studying triangles. Right? He figured out that if you add the squares of the two sides that are not the hypotenuse, they will add up to the square of the hypotenuse. A squared plus b squared equals c squared. Okay? Well, I'll have to use that and figure out what my displacement is. Is Pythagorean theorem hard? No. Okay? It's really straightforward. Right? So calculating the length of this line is just as easy as punching into your calculator for Pythagorean theorem. Okay, so we'll have the square root of 275 squared plus 125 squared. Okay, and so we're looking at 302 meters as my total displacement along that line. Now, what else do I need on that? Because that's just the magnitude. I need direction. And I can't just say northeast, because that's not very specific. Okay? There are 89 northeasterly directions. Okay? I need to figure out which one it actually is. So I need to calculate then this angle here. I need to calculate theta. Now, I've just calculated off the last side on that triangle, so technically could I use any trig function I wanted to find that angle? Yeah, because I have all three sides. Okay. What I generally do, just to be on the safe side, is in case I screwed up this calculation somehow, I use the sides I was given. Okay, just in case. All right. So I have the opposite side of this angle, and I have the adjacent side of this angle. What trig function tells me the relationship between opposite and adjacent? Tangent, right? Okay. So the tan of theta equals the opposite side divided by the adjacent side, right? And I just want to find theta, so I'm going to bring tan over, and theta will be tan to the minus 1, or inverse tan, of the opposite side divided by the adjacent side, okay? Which in this case is going to be tan to the minus 1 of 125 over 275. Okay? That will give me that angle. Okay, so it's telling me it's 24.4 degrees. What's the direction for that? North of east, exactly. Okay, that little angle arc that I drew is touching east, so this angle is measured from or of east, and it's going north of it, so north of east. Okay. Everybody all right with those calculations? Okay. Not too tough, right? It's like grade 8 geometry. Okay. You guys can handle that, no problem. Okay, so this is just the math of what we just did here, just typed out. It's neater than my writing. Okay, so theta, okay, we calculated that, we got all of that other stuff. So 302, I don't know why I have 0.5 here, it should just be 0.4. Okay, everybody okay with how those work? All right, so we're going to try a couple of kind of vector questions like that here. Okay, now. So let's have you guys try this one. It's really easy because these are collinear vectors. Okay, I'll give you a minute on that one and then we'll walk through it. Okay, so this one's pretty straightforward. It's like the most boring town in the world though, okay, with this snowshoe race. So they move forward 10 meters and untie a series of knots. And then they move forward 5 meters. Okay, and again, I'm not measuring these out, but my 5-meter line is about half as long as my 10-meter line. That's close enough for what we need to do. Okay, and then they move forward 25 meters to the finish line. Okay, okay, it's about 5 times as long, maybe. Yeah, that's close enough. Okay, so what's my total displacement? 40 meters forwards. Okay, but that's what our diagrams should look like. All right, questions on that one? I didn't think so. Okay, I would like you guys to try question 7. It's tricky. It's really more of a math trick than it is a vector trick. Let's see how many people we get. I would never ask one like this. I'm going to test. I want to see how many of you get it. Okay, so you got a car that drives north 500 kilometers. Okay, and then it drives 3 sequential displacements south, each of which is 50 kilometers longer than the previous displacement. Okay, the final position of the car is 50 kilometers north of where they started. Okay? Find the 3 displacements algebraically or graphically, whichever will make more sense to you. I don't really care which way. But I'll give you a few minutes on that one because it's a bit tricky. Okay, so the trick to this one is it's an algebra trick. Okay, we know that the car goes 500 kilometers north. Okay, we know it does that. And then we know that after 3 trips, 3 sequential trips, each of which is 50 kilometers longer than the first one, okay, it ends up back here. 50 kilometers north of where it started. Okay, everybody with me there? All right, so here's what I know then about this trip. How long is it? It's 450 kilometers. Okay, that's important for me to know. Okay, and it's the sum of the 3 trips that lead up to it. And those 3 trips can be represented like this. So I can say 450 equals n. That's the first trip. I have no idea how long that trip is. They don't tell me. Okay, but they tell me that the next trip is n plus 50. Okay, and the next one is n plus 100. Because each one was 50 kilometers longer than the one before. Everybody okay with that? All right, so can I move the 50 and the 100 over there? Yes. So I'm going to subtract the 50 and the 100, bring them over, and what I'm going to be left with is 300 equals n plus n plus n. What's n plus n plus n? 3n. Okay, so 300 equals 3 times n. How big is n? 100. Okay, so now I know that n equals 100. So the first trip was 100 kilometers. The second trip was 150 kilometers. The third trip was? There you go. Okay, it's an algebra trick, right? It really wasn't a vector question. Although, drawing the picture at least gets us to that point, okay, where we know what they all added up to.
Like when we were actually like writing it down, should it be like 50 kilometers minus 500? So you would get like minus like negative 450. So you would have like a vector.
Yeah, I mean, we could. I knew that 450 was south. I just kept that in my head, right? Everything in this south, in this trip was all south, so I knew I didn't need to do anything with the vector because they all shared the same one.
I'm just saying, like, when you're like writing it down, like, how do you express it?
You could. You could say plus 500 minus 450. You could say that if you wanted to. Yeah. And like I say, I just kind of kept that in my head that that's what it was. Okay. Try this one. This one involves perpendicular stuff, okay? Because they go south and east and north. All right, so you're going to need to draw the tail to head diagram for this one. All right, so she leaves her tent to go to the lake. She walks 0.8 kilometers south, then 1.2 kilometers east, and then 0.3 kilometers north. We're looking for her overall or resultant displacement. Give you a few minutes on that one. Okay, so what we've got here, guys, is this. Listening, please. We've got 0.8 kilometers south, okay? And we've got 1.2 kilometers east. And then 0.3 kilometers north. Okay, that's the trip this person takes. Everyone okay with that? So if I draw a line that represents their total displacement, that line goes from their initial position here to their final position here. Okay? Now, can I make a triangle out of that line? Yes, I can. A triangle that I would know the sides of. Agreed? Okay, so this side here would be 1.2 kilometers east. And this side here would be 0.5 kilometers south. Okay? You could have also drawn it this way. Okay? You'll get exactly the same answer for the displacement's magnitude, but your angle will be complementary to the one I would get. Because yours would be measured east of south. Mine will be measured south of east. Okay, so it really doesn't make any difference. All right, so I need to find this angle here, and I need to find the displacement, the magnitude there, right? And I have enough information now to do that, okay? This is what we call using vector components, okay? The components of this displacement are 1.2 kilometers east and 0.5 kilometers south, okay? That's what makes up this vector here. All right, so now I'm going to calculate the displacement, okay, by using Pythagorean theorem. So that's going to be 1.2 squared plus 0.5 squared, okay, which should give me 1.3 kilometers. Okay, is everybody all right with that? So that means that her overall displacement is 1.3 kilometers along this line. But I need to know the direction of this line because displacement is a vector quantity. So to find that, I need to use trigonometry to get this angle. Again, I now know all three sides of the triangle. I can use any trig function I want. I'm going to choose tan. Okay? So I'm going to find my angle by going tan to the minus 1 of the opposite side, which for me is 0.5, over the adjacent side, 1.2. And that's going to give me theta. Okay. So, okay, of 0.5 divided by 1.2. Okay, so we're getting 23 degrees. 23 degrees. Okay, so this angle here is 23 degrees. What direction? South of east. Okay, if you got the complementary angle, okay, then you found this one, okay, and it would be 67 degrees east of south. Okay, which would be equally correct. They both tell me the same story. Go that way. Okay. All right, everybody follow what we did there?
Can you just explain why it's south to east? Like
South of east?
Yeah, south
Okay,
of east.
so the angle arc that I drew started at east and went south. So it is south of east. Okay, so whatever I do here, okay, when I write that this is south of east, the second direction is the one I measured from.
Okay.
Yeah? Okay. All right, everybody okay with that one? All right. Now, one like this, these are all collinear. So one like this would be really easy, right? Yes, there's a lot of numbers in here, but it's forward, backward, forward, backward, forward, backward. Okay, we know how to do those ones. Okay, and if I wanted to calculate the total distance, what do I do with all those numbers? Just add them up, right? Okay. I want you guys to write this one down and give it a try. You're going to need to draw it. This is where we're headed to. We have an angled vector this time. It's not perpendicular, okay, like the last one. This one has just an angle on it. So the object first goes north and then turns and goes 30 degrees east of north. Okay, so we need to draw the picture of that and then see if we can calculate the total displacement. I'm going to give you a few minutes to get the diagram drawn, then I'll draw it, okay, and then you guys can see if you get to the math here. Okay, so in this question here, we start out by going 15 meters north. Okay, so there's my 15 meters north. Then I go 30 degrees east of north for another 20 meters. So in order to draw that, what I do is I draw a reference line that's due north because I have to measure east from that line 30 degrees. Right, so I'm just going to do that. That's about 30 degrees, and I'm going to draw a line that's longer than my 15, probably too much longer. That's not really a good scale. Let's try that again. Okay. So maybe, well, put the eraser back where it belongs. Okay, so this one's 20 meters long. This angle's 30 degrees. Okay, where's my line that represents my total displacement? Okay, from my initial position to my final position. Does that make a triangle? Sure does. Okay. Can I figure out how big the two sides are? That's the trick. Okay. I know this part of this side, okay, but I don't know this part. However, I know the hypotenuse of this triangle and an angle in it. Can I find the other two sides? Probably. Okay, maybe using trig, I could figure out the other two sides, and then I would know the triangle for the big red arrow. And I'd be able to calculate how big it is and what direction it's going. Okay? So in other words, I need to know this whole triangle so I can get this angle and D. That's where we're headed. See how many of you can get it. Let's have a look at kind of how we would get going on this one. If I'm going to calculate, okay, the sides of my kind of red triangle here, okay, I'm going to label this side as being Y because it's the vertical one, and this side to be X because it's the horizontal one. That means my blue triangle is similar. It has a vertical component and a horizontal component, or a north and an east component. Okay. Now, if I want to calculate, okay, this side here, the Y, it's adjacent to the 30-degree angle, and I know the hypotenuse. What trig function relates the adjacent side and the hypotenuse? Cos. Okay, cos of theta is adjacent divided by hypotenuse. So I should be able to calculate that. Okay, the cos of 30 degrees should equal y divided by 20. Okay, so if I want to calculate y, I'm just going to go cos of 30 times 20. Your calculator needs to be in degree mode, by the way, if you're doing this. Okay, so that side's 17.32 meters long. Okay, that side, which now means this whole side is how long? 32.32 meters. Can I do the same thing with this? Yeah, I'm just going to use sine of 30, okay, times the hypotenuse, 20, to get x. It's the opposite side. Okay, because the sine of 30 equals x over the hypotenuse, right? So when I do that, sine of 30 times 20 equals x, that's going to come out to 10 meters. No, I didn't just do trig in my head. The sine of 30 is 0.5. That's why I pick 30 all the time, because I can do one of them that way. I did not just do trig in my head. All right, so this side is 10 meters long. So now, do I know the sides of my red triangle? Okay. I know that red y is 17.32 plus 15, which is 32.32 meters. And I know red x is 10 meters. Now I can calculate my total displacement using Pythagorean theorem. And then I can use trig to get the direction after that, just like we did with the camper question. Okay? That part, the end part, is still the same. Right? It's how I get to building that triangle that's a little bit different. Right? That's where we're headed next week. Okay? Is dealing with lots of angled vectors where we're going to have to find their horizontal and their vertical components. Okay? By finding those, we can make triangles out of everything and go triangle crazy and get our hypotenuse and our displacement and whatever else. Okay, so that's where we're going to be going, is using vector components to find the solution. Okay. All right, questions on where we're going from this step? Okay, so I want to find d. Okay, that's going to be the square root of 32.32, okay, squared plus 10 squared. Okay, so my hypotenuse is 34 meters long, okay, and its angle, I'm going to use tan there, okay, the opposite side is 10, okay, divided by 32.32, so my angle is 17 degrees, which way? East of north. Okay, so my final answer here is that D is, what did we say, 34 meters? Yeah, 34 meters at 23 degrees, no, sorry, 17 degrees east of north. All right? Making some sense? We're going to spend a lot of time on this. Okay, because yeah, this is like the trickiest thing, but it's also like the most important thing. Okay, so we're going to spend lots of time on it. Don't worry, you'll get your trig back. Okay, it'll come back to you. Okay, but that's where we're headed to.